Okay, so today we're going to talk about what happens when you have complex eigenvalues and eigenvectors that pop up when you're working with a system of differential equations. So we're still working with non-defective matrices, as you can see. So, we still like those, but we have complex roots of a polynomial, which are not going to be our best friend in this case. We have to do something a little different than we did in Chapter 8, so I just wanted to make a short video doing an example so you would know what to do on exams and stuff. So, for instance, consider this equation here. So we have a 3 by 3 case, and as you can guess, we'll have complex roots. So we do what we do in any other case. We want to find the eigenvalues and the eigenvectors of this. So we have 2 minus lambda 0, 3, 0 minus 4 minus lambda 0, negative 3, 0, and 2 minus lambda. And you set it equal to 0. And there's a lot of zeros involved in this matrix, so the determinant's not too bad. And if you expand it out, you get negative 4 minus lambda, and then you get lambda squared minus 4 lambda plus 13. And so you'll have lambda 1 is equal to negative 4, but here you can't really factor that in your head, so you have to use quadratic formula. And at that point, you'll notice that you'll have complex roots. So you get actually lambda 2 is 2 plus 3i, and then lambda 3 is equal to 2 minus 3i, okay? So that's what you get when you pop out from the quadratic formula. And we saw that in general what you do is you find an eigenvector for each of these, and you stick them all into one solution with undetermined coefficients, C1, C2, and C3, and you go from there. What we'll see that when you're working with complex stuff, you actually only really need to use one of these eigenvalues, and then we're going to be able to turn that one solution into two linearly independent solutions just from working with one. So that's what's a bit different about this chapter. But what we're going to do is we're going to go ahead and find the eigenvectors v1, v2, and v3 anyway, just so we can see what's going on. Okay, so lambda 1 is equal to negative 4. We have a plus 4i, which is 6, I hope. Yeah, 6, 0, 3, a row of zeros, negative 3, 0, 6. So I'm going to take advantage of that column of zeros right here and go ahead and just make this 0, 1, 0 for my eigenvector. Lambda 2 is 2 plus 3i, and this is going to look a little weird, but we might have seen it before. So I have a minus 2 plus 3i times the identity. Gives me negative 3i, 0, 3, 0, negative 6 plus 3i. No, sorry, negative 6 minus 3i. 0, and then negative 3, 0, and 3i. And so since I have 3 eigenvalues up here and a 3 by 3 matrix, I know I should only be able to find one eigenvector associated with this. So I just need to pick one. And so with just a little bit of work, you can see that I don't want to be working with the 6 minus 3i. So I'm just going to go ahead and make the middle term 0 and see if I can get solutions for up here and up here by doing that. And so if I make the first one 1 and the bottom one I, that seems to work out fine for me. So that takes care of the top row, you can see pretty easily. So I have negative 3i plus 3i. And then the bottom row, I have negative 3, and then when I multiply this by I get plus 3i squared, which gives me, oh, sorry, this should be negative 3i, my bad, when you subtract off this 3i right here. So I get minus 3i squared, which gives me plus 3 and gives me 0 as well, my bad. And so anyway, you get this as your v2. And what we see then is that when we're working with complex eigenvalues and eigenvectors, we can actually just say that my eigenvector here is just going to be the complex conjugate of my eigenvector I found for the complex conjugate of this. So all I do is I make all of them the complex conjugate, so the real numbers stay as they are, and any term with an I in it gets multiplied by or gets, its complex conjugate instead of itself. And so this is what we have. We have a V2 and a V3, which is this complex conjugate, and we go from there. So it's technically correct to write our whole solution. So we found everything we need, right? We have 3 eigenvalue eigenvector pairs, so we can stick them all together. So we have C1e to the minus 4t times 0, 1, 0, which was my first pair from up here. I have plus C2e to the 2 plus 3i t times 1, 0, and I, which was my second pair. And then I have plus C3e to the 2 minus 3i t times 1, 0, and negative I. So those are all of my solutions. And this is, technically correct. But the problem that we have here is we have these i's involved. The reason we don't want those is because we have a real valued matrix. So we go up here. There's no i's involved here, right? This is over the real numbers. We don't have any concept of negative square root of -1, right? So what we need to do is we need to somehow get rid of those i's. We don't want those in there. And so we have this nice formula to get an exponent of a complex number down into sines and cosines. So we can go ahead and utilize that. So you remember from earlier chapters, we had e to the alpha plus beta I times t. Based on rules of logarithms, I can break this down: e to the alpha t times e to the beta I t. And these are both real numbers, a and b. So I can just rewrite this as e to the alpha t. And then we had Euler's identity. So we have cosine of beta t plus I times sine of beta t going on with this term here. So this is how we can rewrite this. And so in our case, we have e to the 2 plus 3i times t is e to the 2t cosine of 3t plus I sine of 3t. And so how would that help us at all? Well, what we're going to do is we factor this out into a real part and an imaginary part. So we have this cosine here is completely real valued, and then this I sine of 3t is completely imaginary valued. And so what we can do then is we can also factor out this eigenvector that we have here into its real and imaginary parts. And then when we FOIL all of it, that's where we're able to derive our 2 solutions from. So I have, again, 1, 0, and I. I can factor that into 1, 0, 0. Factor that I out front, and it becomes 0, 0, 1. All right, so I've just factored that vector. And when I multiply this by this, what I end up getting is e to the 2t cosine 3t times my first vector, 1, 0, 0, plus e to the 2t I sine of 3t times my first vector. So I'm just taking care of this vector first. And then my next vector, I get plus e to the 2t cosine of 3t multiplied times I times 0, 0, 1. And then I have plus e to the 2t I sine of 3t times I 0, 0, 1. Okay, so I've just FOILed this out. Sorry if it wasn't super clear, but what you'll notice is I have an I squared term here, which we can rewrite as -1. So I'm just going to do that right here. So my I squareds turn into -1. And what I can do now is I can group my terms that have an I in them, so my imaginary value terms together, and I can group my real value terms together. So I get, this is equal to e to the 2t. I'm going to go ahead and move the cosines and the sines inside of their respective vectors here. So this will become cosine of 3t And then if I subtract off of that minus sine of 3t from down here, because these are my real valued solutions. And then I add on to that I times e to the 2t, my complex valued solutions. So I have now a sine of 3t up here, which comes from this, and then a cosine of 3t at the bottom that comes from this term. And so this is going to be a little weird, but we've actually found two solutions. What we're going to do is we're going to take this to be a full solution here, which doesn't seem unreasonable, right? And then what we're going to do is we're just going to forget about this I, and we're going to take the real part of that to be another solution. Exactly why that works, you can consult the textbook or the lecture notes, but I'm here just to provide an example and some context. So our solution then becomes c1e to the minus 4t times 0, 1, 0. So we still had that real valued solution, right? And then we have plus c2e to the 2t. And then this goes in here. So cosine 3t, 0, sine of 3t. And then plus c3e to the 2t, this part now. Sine 3t, 0, cosine of 3t. And notice how there's no more i's involved. There's no imaginary numbers left, and I have three linearly independent solutions. So I didn't even use this at all, right? I pretty much took this entire part and using Euler's identity, split it up into its real and complex parts by going through and foiling this expression. And now I ended up with three linearly independent real valued solutions. So I'm good to go here. I am done. And that's just a quick example of what happens when you have a non-defective matrix with complex eigenvalues and eigenvectors.